All right, so in this video, we're going to talk about the derivatives and integrals dealing with these hyperbolic functions. And instead of having to write all of these out, they're very clearly marked in your book on page 429, tables 7.7 and 7.8. So I'll give you an opportunity to review those. But because many of the identities were slightly different, and that's again all caused because of the fundamental identity being a little different, which again is caused now by us dealing with a unit hyperbola instead of a unit circle. Many of these derivatives are similar, but slightly different as well. So you want to pay real close attention when it comes to these and how they are a little bit different than what you might have expected coming in. Again, I'm not going to write them all out, but I do just want to focus on some notation for a second. For example, of the hyperbolic cosine function, so cosh of x is actually equal to sinh of x. Okay, now we've got a derivative definition now that we're going to prove here in just a second. But if you remember how we did this also in Calc 1, if I go ahead now and I move the dx to the other side, then I'm going to have d cosh of x equals sinh of x dx. Now when I integrate both sides, on the left, the antiderivative and the derivative do away with one another, leaving me with the integral for sinh of x dx being equal to cosh of x dx. So once again, I just wanted to review with you how the derivative related to the antiderivative, and you can certainly see that in all of the other ones as well. So again, just more of a review for notational purposes. But that being said, I do want to come back and I want to prove this original derivative. Since they're a little bit different, I think it's important to see and at least justify why they are what they are. Now, conveniently, we also have a exponential definition for cosh. The definition of cosh would be this e to the x plus e to the negative x over 2. And if I go ahead now and take the derivative of this, maybe I'll rewrite it so it's a little bit easier to see. That's just going to be a 1/2 e to the x minus 1/2 e to the negative x. And when I put all this back together, it's pretty evident that that's going to be your sinh of x. So again, nice justification as to why it might be a little bit different, but at the end of the day, now you have a good understanding of why it is what it is. All right, I'm going to go ahead and prove one more for you, a little differently, but either way, it's going to be important to kind of see where this all comes from. We're going to prove that the derivative of tangent, hyperbolic tangent, is going to be equal to hyperbolic secant squared of x. So now, the proof is going to be where we take the derivative, not so much of hyperbolic tangent, but as we talked about before, that's going to be sinh of x over cosh of x. And now, since we're pretty clear on the derivative of sinh and cosh, we can go ahead now and use a quotient rule. So we've got low derivative high, which would be another cosh of x, minus the high and the derivative of the low, which would be a sinh of x, all over low. So in the numerator, this is going to be cosh squared of x minus sinh squared of x. And if you forget those h's sometimes, it's easy to do, just go back and put it in there, over cosh squared of x. Now we have our fundamental identity in the numerator. So we've got a 1 over cosh squared of x, which is of course going to be your hyperbolic secant squared of x. So even when we proved this in Calc 1 for our unit circle trig functions, we looked at them a couple different ways. We're still able to essentially do the same thing here, but now we're just being with the understanding that we're dealing with a unit hyperbola instead of a unit circle, and things could certainly be a little bit different. Okay, so we'll take a look at an example here. And we've got our function being the hyperbolic secant of e to the 2x, and we're going to find its derivative. And so if you remember, if you can look back even if you need to at this point, the derivative of the secant is going to be negative secant tangent. So we want to be a little bit careful with that. So negative hyperbolic secant, keep the inside the same. Hyperbolic tangent, keep the inside the same. Back times the derivative of the inside, which would be e to the 2x times 2. So there's an unsimplified derivative there. Again, you're not doing anything different, but you just need to make sure the derivatives that you take are in fact correct since we're dealing with hyperbolic functions. Integration is really no different. Let's take a look at one here. We'll take the hyperbolic cotangent squared multiplied by the hyperbolic cosecant squared dx. And so, again, think easy here, all right? This one actually is a nice u sub. If we let u equal that hyperbolic cotangent of x, then the du, again, be careful with your signs in particular, we still have that negative hyperbolic cosecant squared dx. So it's a good fit. We'll just have that negative now off to the side with a u squared du, and then integrate as usual. Negative 1/3 u, and our u was the hyperbolic cotangent cubed plus c. So again, these two examples are very, very simple in the sense that you're not doing anything different other than making sure you're using the correct hyperbolic derivative and integral formulas that we talked about in the last slide. Okay, so I'm going to go ahead and clear the screen and work one more really interesting example with you, and hopefully it'll tie some things together. Okay, so being where we are in the section dealing with hyperbolic trig functions, it probably makes sense to at least have that in the back of your mind. And so if you look at this and the definitions from the beginning of the section that we talked about, you could jump to the conclusion pretty quickly that this is going to be the hyperbolic cotangent function. And so to integrate this, we'll integrate it similar to how we did tangent or cotangent earlier in the course. This is going to be cosh of x over sinh of x. And now we're ready for a u sub. If u equals that sinh of x, our du is going to be cosh of x dx. And the integral is quite simple. A 1 over u du, which turns into the natural log of the absolute value of u, and u is sinh of x. And we don't want to forget our plus c. Okay, so this is a perfectly reasonable answer. Now, the reason why I like this particular problem is because there's not always one way to do something, and the results can be gotten to differently, but they still need to be the same. So I'm going to rework this another way, and some of you might have seen this to get started. From the very, very start, if I let u equal e to the x minus e to the negative x, so if I let my u from the start be this bottom piece, then my du would be e to the x plus e to the negative x dx, which is actually a perfect fit for the numerator. So that leaves me with this 1 over u du, which is the natural log of the absolute value of u, which is e to the x minus e to the negative x plus c. So we got to an answer two different ways, but like I said before, they have to be the same answer. And so I guess the question is, can you be convinced that this guy is the exact same thing as this? Well, let's go a little further with this one right here. Okay, so if I take this now and I change this into its exponential definition, I'm going to have the natural log of the absolute value, e to the x minus e to the negative x over 2 plus c. So you're probably a little closer in believing that this is equal to this, but we still have something that looks a little different, right? We have this 2 right here. Well, remember, you've got properties of logs. And so in theory, because we're dividing, we can now subtract that natural log of 2 off. And we're one step closer now, but you still might be asking yourself, wait a second, you still have this here now, but not up here. True, but this is a constant. So I'm going to be able now to take this constant and combine it with another constant into a plus c, a single plus c. So when I take these two things now and I combine them, that whole thing can go to a plus c, in fact showing that this answer is the same thing as this. And so I show you this not so much because you have to know both ways. I think it's good if you know both ways. But when you start to check your answers, you might have one thing, the book might have another, but you both might be right. So take some time and really convince yourself of what's going on here. Chances are it's just a little bit of algebra in there that you can certainly work through. But nevertheless, it's a really nice problem to discuss.